each limit below, if it exists, determine the value using the associated graph. So our first one, limit as x goes to 0 of 2x over x. Well, that one's pretty easy. It's clearly going towards 2 because it's just steady state at 2 all the time. While at actually plugging in 0, if we plug in 0, 2 times 0 over 0 gets a 0 over 0. We can't plug in 0. So it doesn't exist at 0 over 0, but on the way to that x equals 0, it exists just fine. So we can see what the limit that it's going towards is. So the limit that it's going towards is 2. Similarly over here, limit as x goes to negative 2 of negative 3x minus 6 over x plus 2. What is it going towards? It's going towards that thing, which is negative 3. So it is going to negative 3. If we actually plugged if we actually plugged negative 2, right, if we plugged negative 2 in, well, x plus 2, so negative 2 plus 2, we get us dividing by 0. Things would fall apart. We're not allowed to do that. But as long as we're not plugging in negative 2 directly, everything's fine, right? We always wind up having negative 3, as we can see from this picture right here. So since it's always negative 3, then the limit of what it's going towards, we don't have to worry about that thing that's actually at, the limit of what it's going towards is negative 3. Simple as that. Also, I want to point out to you something that we're going to see in the finding the values of limits. We can actually get a jump start on what's going to happen to get that idea percolating through your head. Look, 2x over x, well, at x equals 0, it winds up doing something different. But with the exception of x equals 0, 2x over x behaves exactly like 2. So because it behaves exactly like 2, we can effectively say, well, what would it be at 0 if we were using this other alternative way of talking about it? The other alternative is you're always 2. So since it's always 2, we wind up getting a limit of 2 out of it. Same thing going on over here with negative 3x minus 6, negative 3x minus 6 over x plus 2. Well, we can rewrite that top as negative 3 times x plus 2 over x plus 2, which means we can then write an equivalent thing with the exception of x equals negative 2. Everywhere else, we won't have that issue. It'd just be the same as negative 3 forever and always. So with the exception of that x equals negative 2, it works just fine, but we don't actually care about negative 2. Remember, there's that idea of blacking out, right? We're covering up that chunk because we're not allowed to peek underneath the cover. So if we cover up that chunk, and then we try to figure out, well, where is it headed towards? We don't have to worry about the fact that if we had plugged in negative 2 here, it wouldn't work, because we're not worried about what happens at negative 2. We're just worried about what happens everywhere else, and what it's equivalent to everywhere else is negative 3, and so that's why we wind up seeing it. Just a quick preview of the ideas we'll wind up getting when we start talking about finding limits precisely with more algebraic methods. All right, so that gets us a really good idea of how limits work. Just remember, it's the idea of where are you going and does it match from both sides. The question of where you're going, but it doesn't matter what it actually is there. It's about the journey, not the destination. All right, we'll see you at Educator.com later. Bye.